Okay, this unit's going to be test 1E material. It's still kinematics, but it's two-dimensional kinematics. We talked about how we can add two vectors together to create a vector sum, otherwise called a resultant. We can do it backwards. You can also reverse that process, and from a vector you can find what we call its x and y components. In other words, we will teach you how to resolve a vector into its perpendicular x and y components. Okay, for example, look at this. I have a dog on a leash, and I'm walking that dog, and he's resisting. And here's a force that I'm applying to his collar through the leash. Okay, so force is a vector. We haven't talked about that yet. Forces are push or pull in some direction. Let's say I'm pulling on his leash with a force of 20 pounds. Okay, there are two components of that force. And I can break that force up into its x and y components. So it has a vertical component that tends to pull the dog upward, and it has a horizontal component that tends to pull the dog forward. Okay, those two together are the x and y components of the force I'm applying to the leash. Okay, so look on the picture on the left here. Here's the force I'm applying at some angle. I use theta for the symbol theta for the angle, and I draw a box from the tip of the force that I'm trying to break into its components and to the x and y axis. Okay, so here in green is the y component of the 20-pound force, and the blue horizontal component or x component. So these also are called horizontal or vertical components. And the y is called the vertical component. So sometimes we use that terminology instead of x and y components. Now, what I do is I bring this vertical component over to make a right angle triangle. So here we go. Got cut off here. Here's the force. And here's the horizontal component, Fx. And here's the vertical component. I moved it over to this side right here to make this right angle triangle. And let's call that FY. And here's the angle. Okay, so this is a right angle triangle. Okay, so what we can say is this force is the vector sum of its components. So the slanted force, or the slanted vector, is the vector sum of its x and y components. Or the resultant force, or whatever vector it is. You can do this with velocity, you can do this with acceleration, you can do this with displacement, any vector. So F is a vector sum of its x and y components. Okay, so we're going to be basically using velocity, only using velocity with this method because we're still on kinematics. We're not talking about forces yet. I just gave you that as a practical example. So here's my velocity, the red arrow, and I've broken it down into its x and y components. So V is the vector sum of Vx and Vy. Now, that does not mean that V equals Vx plus Vy. It's a vector sum. And so we use Pythagorean theorem to describe the relationship between the resultant vector and its x and y components. And there it is right there. Okay, now remembering our trig, the opposite side, we take our angle from the x-axis. We take our angle from the x-axis. This is always going to be true. Vy will always equal the opposite side, and Vx will always be equal to the adjacent side. Okay, using a trig function, sine of theta equals, in the blue box right here, sine of theta equals opposite side over hypotenuse. Cosine of theta equals the adjacent side over hypotenuse. We can solve for each of these given the resultant vector. So Vx would equal the adjacent side, so that would be cosine of theta times V. Or V cosine of theta. I would just memorize it. Vy equals the opposite side always if your angle of the resultant velocity, if the angle is from the x, taken from the x-axis. You can do this. That'd be V sine of theta. Be sure you're on degrees on your calculator when you're doing this. The mode should say calculator. Should say degrees, not radians. So this will always be true in the yellow box. if your angle's from the x-axis. So, here's an example. Okay, so I sketched that out. Here's V, 14 meters per second, angle of 25 degrees from the horizontal, so from the x-axis, where horizontal and vertical components of its velocity. Okay, so I draw a little box. Okay. I realize that all my vectors point from the origin. Okay, so the direction is important. Okay, so I did all that. I'm gonna move this guy right here over to that end. So I'm gonna go okay, here's Vx, here's V, then I'm gonna move that guy over here. Now my right angle triangle. And so right here, the y component is the opposite side, so it's V sine of 14. So Vy is the opposite side. So Vy is V sine of theta is equal to 14, which is V times sine of 25. Vx is the adjacent side, which is equal to 14 times cosine of 25. So, sure your calculator's mode is on degrees, not radians. So I get the y component is equal to 5.92 meters per second. And then I get the x component to be equal to 12.7. Okay, so I'm sure you can do that on your calculator. Okay, so this is just a repeat of the same thing. So we got that's F, the net force or resultant force. This be called Fx. Here's the y component Fy. Move the Fy to make a triangle. Okay, then solve for the x and y components, except that this would be Fx, this would be Fy, this would be F instead of velocity. So same thing here. No, I should have said this. Newtons is the unit for force. It's about a quarter pound. Newton size. So Newton is the unit that we use in physics for force. So that's why you're seeing that capital N there. So to find the x and y components, I move that Fy over to the opposite side. And then I use the trig functions to find the answers. Okay, so 26, eventually you don't even have to draw this. So 26, and you go 41, and they want the horizontal component only. So they're looking for this piece that is the adjacent side, and that'd be the V times cosine of theta, 26 cosine of 41. And I get 19.6 meters per second, which rounded up to 2 sig digs is 20. What's the vertical component? Same idea. Okay, so 26 meters per second is V. I'm looking for the vertical component this time. This is 41 degrees. I move this over to the other side and I realize that that's the opposite side. Right here. And so that's V times sine of theta. So 26 sine of 41. 26 sine of 41 comes out to be 17.1. So running up to 2 degrees, I get 17. Okay, so we have force 35 degrees east and north. Okay, so be careful. Here's 35 degrees. East of north. So here's north. Here's east. So here's that force, 280 newtons. Okay. What is the eastern component? So we're looking for Fx. Eastern component. The horizontal component. Now be careful, because what's going to happen, I don't want the angle from the y-axis, I want it from the x-axis. So you go, it's complementary to the angle from the y-axis. So you go 90 minus 35. The complement is 55. So now you can kick in Fx is equal to the adjacent side. So that'd be F times cosine of theta, but with 55 instead of 35. So it'd be 280 times cosine of 55. So I get 161. Now, if you want to use 35 degrees, you could. I mean, no one says you can't. Then you can say it would be the opposite side. So fx would be the opposite side, which would be relative to this 35 degrees angle. So this would be sine of 35, f sine of 35. And it would still be equal to 161 newtons. But I like to always use the angle from the x-axis. Okay, what is the northern component of a twig? Okay, so basically you're looking for the Fy in the same picture that we just did. So I'm using Fy with the blue, the 55 degree angle would be the opposite side. So that'd be F times sine of theta. That would be 280 sine of 55. 280 sine 55 is 230 or 229.3. I don't know why they're not rounding off to 2 digs like they should, but that's my answer. Okay, so that was just the background. Now we're going to use this component method to solve for projectiles motion in 2 dimensions. Okay, so let me just, this thing looks a little confusing, but let me just talk about this a little bit. If you throw an object into the air, and you just don't throw it straight up, you give it some forward velocity, so you shoot it forward. Let's call it original velocity. It has 2 components. A part of velocity, the x component, causes it to move forward in space. And the y component, if I threw it up an angle, some launch angle, causes it to rise. So when you launch a projectile, it has both x and y components if you launch it at an angle upwards like that. The x component causes the projectile to move forward. The y component causes it to rise. So, this is what we're gonna, when an object's free falling, the only force acting on the object is its what? Okay, so here's the object. The only force acting on the object is its weight. Okay, so the only acceleration acting on the object is g. And that's an acceleration in the y direction. There is no acceleration in the x direction. Now, why is that? It takes a force to cause an acceleration. The only force acting on the object is its weight. So once it leaves your hand or your foot or the baseball bat or the lacrosse racket, whatever, the only force acting on it is the weight, and so there's only The weight causes a downward acceleration. We'll call that A in the y direction. And there's no A acceleration in the x direction. That's important. So on Earth, AY will be negative 10, close to Earth, and AX will be 0. Okay, let's forget that for now and go to what I was just talking about before this. So when you launch something, it call that VO. There's X and Y component, blah, blah, blah. Okay, I just mentioned that. Okay, we're going to start off easy with projectiles that are horizontally launched. There's no launch angle, like I was just talking about. The launch angle is 0. Okay, it's horizontally launched. Okay, so when that happens, the very moment it's launched, there is no y component. So VOY is 0. And the original speed is the x component, is all in the x component. There is no y component, as you can see in this picture right here. Then we can say the acceleration is AY is negative 10, at least on Earth, meters per second squared. Okay, how does Vx, Vy, and V change? The net velocity, how does that change with time? Okay, so the Vox stays. The Vx stays the same. So you can see right here, the Vx remains the same throughout the whole trip, unless there's air drag, and we assume there isn't. So Vx remains constant. Why? Because AX is 0. There is no acceleration in the x direction. The Vy continues to get bigger and bigger by 10 meters per second every second. As you can see in the diagram here, the y component continues to increase by 10 meters per second every second, at least on Earth. So the resultant velocity, shown by the black arrow in the middle, the resultant velocity keeps on getting larger and larger as well, because the y component is getting larger. And then the angle from the horizon, this angle right here, keeps on getting bigger and bigger. Okay? Now, this picture is showing a strobe light picture. So, I drop a ball. The red ball is dropped. From rest. And the blue ball is thrown horizontally from the same height. Okay. So both hit the floor, if I dropped the ball at the same time that I threw a ball horizontally from the same height, they would hit the floor at the same time because they both have the same VOY, VOX, and they both have the same VOY, which is, in this case, is 0. I didn't push it, I didn't throw it upwards or downwards, I just dropped it or threw it forwards horizontally. So VOY is equal to 0 and AY is equal to -10. So it's important for you to realize that. So wait, this is a strobe light. It's flashing, like, let's say, every 10th of a second in a dark room, and your camera is trying to take a picture of this, and so the shutter stays open on your camera. Every time there's a light flash, it picks up where the ball's position is, and then after maybe a second, the camera clicks, the shutter clicks close, and you got images where the ball was every 10th of a second. Okay, the point is, both balls drop at the same rate. Okay? And we'll hit the ground at the same time if dropped from the same height. One's thrown forward, one's just dropped. Both have the same VOY. One has VOX. The blue ball has a horizontal velocity at the beginning, which maintains throughout the whole trip since there's no drag. And the red ball has no horizontal velocity. Okay, what I'm trying to say also is that the vertical and the horizontal motion of a projectile are independent of each other. The horizontal velocity does not affect the vertical velocity, and the vertical velocity does not affect the horizontal velocity. Let's do a problem. A line leaps horizontally from a... Okay, so this is the height. Okay, 7.5 meters. And here's the line going straight forward. So that's 4.5 meters per second. No vertical velocity. Okay, the cub jumps the same way. The speed of 1.6. Which one reaches the ground first? Well, if they jump from the same height, and they were both going horizontally, they had the same EOY. which is 0. They both have the same AY, which is -10. So they have to hit the ground at the same time. It doesn't matter how fast forward they go. So it's letter C. Y, the horizontal and vertical velocity are independent of each other. Okay, so the same case, 2 marbles roll off the table. Okay, blah, blah, blah. Which are the same for both well, we know AY is the same. We know VOY is the same, which is equal to 0. AY is -10. The final speeds of the marble? No, because when that marble hits the ground, the one with the bigger VFX, they both have the same VFY. The one with the bigger VFX will have a bigger final velocity. Okay, the one with the smaller VFX, same VFY, right? We'll have a smaller VF. So it's not that one. Yeah, they both hit at the same time. No. The one that, here's the distance from the table. I'll call that dx. The one with the bigger forward speed will have a bigger range, or dx, so it can't be that one. But other right answers are AY and VOY are the same. Okay, so let's do an actual problem. A cannonball is shot horizontally from a cannon at a height of 15 meters. Okay, I'm going to call that dy, or delta xy, really, which is confusing, so I'll just call it dy. No, let's call it delta y, because that means vertical displacement. Okay, here's the cannonball. That's 15 meters high. Okay, the VO is 20, but that's also equal to VOX. How far away does the cannon fall? So it's going to go. So I'm looking for dx, which is delta x, that distance right there. Well, it's the displacement, so, and dy is, or delta y, is the height in that direction. Hey, how far? Okay, let's just compare the x and y values first of all. AX, what does AX equal? Very important. AX is equal to 0 because there's no force pushing it forward. AY, that equals -10. The force pushing it downward is the weight of the cannon. With VOX, that's 20. Okay, VOY. Well, if it's shot horizontally, That's 0. What's VFX? Well, VOX does not change at all because AX is 0. So that has to be 20 as well. What's VFY? I don't know. I'm going to have to figure that out. But we've done that before with free fall. What's delta X? I don't know. We're going to have to figure that one out too. What's delta Y? It's negative 15 because start to the finish is downward. That's what displacement is. The direction from the start to the finish in the direction of the finish. What's the time? That's what I don't know the time. I don't know the time in seconds, but the time it takes to go forward is the same as the time it takes to go downward. So the time's the same for both. Okay. Okay, so let's solve this. I usually try to find the time first. And how do you find the time? That's the first step. Find the time if they don't give it to you. You use the values that they give you more info about. Okay, so looks like I got more information because these are the same. This is not going to help me. I got more information with the Y values. So what's an equation using the Y values? What's an equation I can use that will find me time? Okay, so A VF VF. Okay, so I can do A equals VF minus VO over T. So I use the Y values. It's probably good to put the X and Y's there. I mean, it's probably essential that you put the subscripts there so you don't get confused between the two when you're plugging into the equation. So negative 10 equals, I can't use that one because I don't have VFY. Okay, so back to the drawing board. That's another equation I can use. Let's see. I got VF. Okay. How about this? VF squared equals VO squared plus 2A delta Y. Okay, so VF squared, I don't have, but I can find there. Then I can find the time. Wow. There's probably an easier way, but let me just do this. VF squared equals, I'm just using the Y values. So, what's VOY? That's 0. AY is negative 10. And delta Y is negative 15. So VFY squared is equal to 20 times 15 is 300. 20 times 15. Then two negatives cancel out. So VFY is equal to square root of 300 equals 17.3. Okay, now I can go back to the original equation and find the time. So I'm going to go back to this now that I have v of y. So negative 10 is equal to v of y. V of y is 0 over time. So 10t I'm sorry, v of y has to be negative because it's going downward. We're talking about velocity. So negative 10t equals negative 17.3. Divided by t. So get rid of the negatives. 10t equals 17.3. The time is 1.7 seconds. Okay, that's a two-step process. There's an easier way to do that, and without having to do two steps, I could have used d. I could use d equals VOT plus AT squared over 2. I thought I was kind of shying away from that because I thought it was going to use the quadratic formula, but it doesn't. So because v of y is 0, so it knocks that totally out. Okay, so 30 cross multiply. You don't have to, you could say just 5 here. So negative 15 divided by 5 is 3 is equal to t squared. So t is the square root of 3, which comes out to be 1.7 seconds again. So that would have been an easier way to solve for time. But all these equations are related, so no. I just solve for the time. If you look, what we're trying to find, how far away will the cannonball land? So basically now I have to go and solve for delta x. So I'll use the same equation I did up here, but use the x values. Okay, so delta x, that's what I'm looking for right here. The range is VOX, which is equal to VO 20. I have the time, 1.7. AX is 0. So that whole part cancels out. So 2 times 1.7 is 3.4 times 10. So that comes out to 34 meters. Okay, so after you find the time, you can find anything. Okay, so baseball's thrown. This is VOX. So VO equals 44, positive always. Tries horizontal distance, so delta x is equal to 18 meters. How far does it drop during its flight? So I'm looking for delta y. course, I gotta find time first. Okay, let's see what else we know. So VOX is 44. VOY is 0. AY is -10. AX is 0. That's about all I know. So I should be able to find the time first using the values that I have more of. So I know more. I know more of the X values because I got 2 non-zero numbers. I got only 1 non-zero number in the Y values. So let's solve. So how can I find? Let's see. So let's do what we did before. Delta X equals VOT plus AT squared over 2. Doing the X values. So 18 equals 44 times time. Remember, we're always trying to find the time first if it's not given. And then AX is 0. Okay, so AX is 0. So it cancels this whole term out. AX is 0, right? So T is equal to 18 divided by 44. Divided by 44 is 0.41 seconds. Now they found time. I can find anything else. So how far does the ball drop during its flight? So what I'm going to do next is use the same equation that I just did, but with delta y. Okay, so VOY is 0, right? So delta y equals AY, which is -10, times t squared, just found time, 0.41 squared, over 2. So -5 times 0.41 squared. Comes out to be 0.84. -0.84 meters. Okay. How about another one? Drops of fish. So it gave me delta y travels. So he gave me delta x. It was Pelican speed. So I'm looking for VO, which is basically VOX. Okay. So so this looks like it's going to be pretty easy. First of all, I got to find the time. Which do I have more of? Okay, so y equals VOYT plus AT squared over 2. AY t squared over 2. Okay, VOY is 0. So this is the equation I'll use once I find time. Well, let's try to find time with the x values. Delta x equals VOXT plus AXT squared over 2. AX is 0. So it knocks that stuff out. So I got 9.3 equals VO1, VOX, I mean, which is, that's what I'm looking for. So I'm kind of stuck with that one too. So let's try something else. How about, So let's go back to this equation right here. We got negative 8.1 equals negative 10 over 2 times t squared. So I can find t. This is what I have to find first anyway. Once I find the t, I'll plug it in here. And I'll solve for VOX. Okay, so t squared equals 8.1 divided by 5. The negatives canceled out. I made that 5 right there, negative 5. So t is equal to square root of 8.1 divided by 1.62, and then square root that, 1.27. Now that I got that, I'll plug it in there. So I get 9.3 equals VOX times 1.27. VOX equals 9.3 divided by 1.27. I get 7.32 meters per second. That is equal to VO. Okay, so instead of making a chart, which is kind of time consuming, you kind of just think it out. Trial and error. Okay, the next section we do, the final section, is when we launch, talking about projectiles launched at some angle, some launch angle, like we have in the far left over here. Okay, so notice what's different from this and the horizontal launch ones. Well, we can see VO is not horizontal right here. VO is not horizontal, it's launched at an angle. So VO is not going to equal VOX anymore like it did in the horizontal launch problems. VOX is going to equal V, because it's the adjacent side of this triangle right here. There's the launch angle theta. Here's VOY, VOX. So VOX is going to equal VO because it's the adjacent side. VO cosine of theta. VOY is not going to equal 0 like it did before. VOY is going to equal VO sine of the launch angle. So that's a big difference, and you got to do that at the beginning if it's not done for you. So I can't stress more that difference. Okay, notice that the Vx component stays consistent throughout the whole entire trip in the air. Okay, so Vx is constant. Why? Because Ax is still 0. Now Vy decreases to 0 at the top and it becomes negative. Okay, so Voy, you can see this arrow is decreasing until the top. The top, Vy equals 0, like they say right there. But then after it goes past the highest position, after it passes that, Vy becomes negative, okay, because it's pointing down. So that's an important concept. Vy becomes negative. Okay, so we just did that one. Okay, so if you hit horizontal ground, look, it's symmetrical. So your V right here is the same as the V right here in size. Okay, so at any level, on the way up and the way down, you have the same V. Because Vy is the same and the Vx is the same, but Vy is in the opposite direction. So this Vy is this Vy at the same height, are equal in magnitude but opposite in direction. V reaches a minimum at the top. So V equals Vx, which at the top, don't say it's at rest, that V is 0 at the top. Vy is 0, but V is equal to the x component of the original velocity, or any velocity, because it stays the same. Okay, and then I said this already. Ignoring air resistance, the horizontal component of a projectile's velocity, so Vx stays constant because Ax is 0, that's why. Now if there's air resistance, it would continuously decrease, but usually we say air resistance is negligible. When a football on a field goal attempt reaches its maximum height, how does the speed compare to its initial speed? Well, it's always less. It's not 0. It equals the Vox. So V at the top is equal to Vox because there's no Y component. So it's less than its initial speed. Okay, its initial speed is Vo. Vox is always going to be smaller than Vo. And launch an angle. Voy turns to 0. Vox is the same, but Vox is smaller than Vo. ignoring air resistance, the magnitude of the horizontal component. So that's AX. We know it's 0. The magnitude, the size of the horizontal x component of the acceleration AX. If a ball is thrown with a velocity of 25, what is the vertical component of the velocity? So they're asking VOY at that moment. And I know that's V. It's the opposite side, so sine of theta. So that'd be 25 sine of 37. 25 sine 37, using my calculator. Using my calculator to solve it, I get 15.0. 15.0 meters per second. If a ball is thrown with a velocity of 25 meters per second, angle, what is the horizontal component? Okay. Horizontal component is the adjacent side, so that'd be V cosine of theta. Okay, so it's at that moment. So again, well, it stays the same throughout, so that doesn't matter. So looking for the horizontal component is VOX. VOX equals V cosine of theta. Velocity is equal to 25, the original velocity, times cosine of 37. 25 cosine 37, 19.96, so about 20. If a ball is thrown, okay guys, I'm just doing the first step of these problems over and over and over, where you have to break it down, the velocity, the slanted vector VO into its x and y components. That's what I'm doing. I'm practicing over and over. Okay, so this is VO. This is the angle from the x component. I mean, for the x-axis. What is the horizontal component? So I'm looking for VOX. VOX equals VO cosine of theta. Adjacent side, like we just did. So 25 cosine of 53. I get 15. Okay, so ball is thrown with the velocity. And this is repetitive. Here's VO. Here's an angle. What is vertical component? VOY. VOY is the opposite side. So it's VO sine of theta, which would be 25 sine of 53. So 25 sine, I get 20. Finally. Oh, this is different. What is the horizon of its instantaneous velocity? The moment it's at the exact top of its trajectory. Trajectory means the path. So right there, VO, you should know that V at that point is only the x component. It's the same as the x component. at the beginning. So it'd be VO times cosine of theta. So 20 times cosine of 60 is 10. Okay, now we start doing real problems. All that was just preparatory. Determine maximum height reached by, okay, delta y is what we're looking for. Okay, so at that point, let's just call it, I know that, let's call that VF, because we're finishing it right there. VFX is equal to VOX. So we'll have to find that. VOX is 30 VO times cosine of 30. Because that's the angle down there. So 30 cosine 30 is 25.98. So let's just call it 26. Okay, so VOY, let's find VOY over at it. VOY is 30 sine of 30, which is 0.5 times 30, which is 15 meters per second. So we know that. We know AY is negative 10 meters per second on Earth. You know, AX is 0. And we gotta find time, just like we did before. Okay, so that's my objective. My primary objective is to find delta y. So delta y equals VOT plus AT squared over 2. And put y's in for everything. And so I got VOY. Okay, I have VOY. I don't know what T is. I have AY. Again, I don't know what T is. And I could solve this using quadratic formula. But I don't really feel like doing it that way. Okay, so how about let's try a different equation with y values. How about VX squared equals VO squared plus 2A delta. I'm using the y values, so it'll be delta y. So this looks good. VFY squared, I know, is 0. That's important. Do you understand that? At the top, VFY is 0. Because this bead goes 0 in the y direction at the very top. So 0 equals VOY is 15 squared plus 2 times negative 10 times change in y. Okay, I'm almost there. And I didn't have to find the time. I didn't have to find the time using this. So my idea of you gotta find the time, is not always true. Okay, so sorry about that. So 15 squared equals 20 delta y equals 15 squared by 20 equals 11.3. So it attained the height of 11.3 meters. That's the maximum height it attained. Okay, so let's just look back here. And I really couldn't use this equation anyway because I didn't have the time. So I used the other fancy equation. How about this one? Okay, so here's VO. Here's the launch angle. So maximum horizontal distance, I want delta x. Okay, so here's VO, here's the angle, and here's delta x. So I need to break this VO up in x and y components. Let's just do it, okay, even if we don't need to. VOX equals VO cosine of theta. VOY equals VO sine of theta. Okay, so VO is 50 times cosine of 30. Other one is 50 sine of 30. That one's 0.5 times 50 is 25 meters per second. And 50 cosine is 43.3. And the y component, the original velocity, is VO sine of theta, 50 sine of 30, which is 25 meters per second. Okay, so we're trying to solve for delta x. Okay, we really need to find time. And to find time, it's kind of a trick. You use the y components of the original velocity and realize that at the top, VFY is 0. So what we're going to do is solve for the time it takes to go to the top. And then I'm going to double that time for the time to figure out the time it takes to get to the end of the trip. So, okay, so A equals VF minus VO over T. I'm going to use the Y values. So negative 10 equals, VFY is 0 at the top, minus VOY is 25 over T. So T 10T is negative 25. Negative 10T is negative 25. So T equals 2.5 seconds. No, the total time, that's the time to get to the top, 2.5 seconds. The total time is twice that, because the halfway point is 2.5 seconds. The total point where it hits the ground is the time it takes to go from launch to hitting the ground is double that, is 5 seconds. Okay, so now we can solve for delta x. Delta x equals VOX, which is 43.3 times the time plus AX. Ooh, AX is 0, right? So it cancels out that whole term. So we found the time already. The total time is 5. So delta x is 43.3 times 5. 206.5 or 217 meters. Okay. What is the highest the cannonball gets? Okay, so that's VO. The angle is 20 above the horizon. Here's VOX. Okay, let's find VOY and VOX. VOY equals the opposite side, VO sine of theta, equals 60 times sine of 20. Then VOX, we might as well find that. VO cosine of theta equals 60 cosine of 20. Sine of 20. 20.5. 60 cosine of 20. 56.4. Okay, so first I have to find the time. So you gotta realize that at the top of the thing again, of the trajectory, VFY equals 0, and VFX is equal to VOX. Okay, so we can do this simple equation. A equals VF minus VO over T. Use the Y values. So -10 equals VFY 0 minus VOY, which is 20.5 over the time. So the time equals 20.5 divided by 10, which is 2.1 seconds. Okay, now that I got the time, I can solve for delta y. I think the highest t equals VOT plus AT squared over 2 put the y's in. That's what I'm looking for, the height, maximum height. So VOY is 56.4 times the time that I just found, plus AY, -10 times 2.1 squared times squared divided by 2. And I get 96.4 meters as the maximum height. How far downrange does the cannonball land at this time? At the same height that was launched. So basically, I'm just saying over level ground. So what I'm asking for is what's delta x for the entire trip. So that's easy. I use the same equation. VOT plus AT squared over 2. I'm using x values, and AX is 0. AX is 0. So it cancels this whole term out. So delta x equals VOX, which is 56.4 times the time, which I already found, 2.1. Let's be careful. Let's be careful. No. 2.1 is the time it takes to go to the top. So this total time, this time is 2 times the time it takes to get to the height. So very important. So so this time right here is the total time. So this would be, this time we found right here is halftime, the halftime. So T total would be 4.2 seconds. So I'd have to put that in right here. Almost made that mistake. So 56.4 times 4.2 is 237. Okay, so this is pretty common sense. The more vertical launch angle, so the steeper the launch angle, the bigger will be the VOY, smaller will be the VOX. So the bigger the VOY is, the higher it will go, and the longer it will be in the air before it hits the ground. So, but obviously, if you shoot it too high, it's not going to go so far. But the smaller the elevation angle, the launch angle, the smaller the launch angle, the lower less high it will go, and the shorter time will stay in the air. So my next question will be, what angle will give you the maximum range? Okay, so we're finding two things. We want it to be in the air the longest time for maximum range, long time, but you don't want it to hit the ground right away. So, from common sense, and we can do a simulation in class. From common sense, 45-degree angle gives you the optimal range. The optimal range is produced by, for a given speed, the maximum range will happen when you shoot it at 45 degrees to the horizon. And then you can use this and see for yourself what angles result in the same range. You're going to find that complementary angles give you the same range. So if you shot something at 30 degrees for the same, it went like that. For 60 degrees, which is complementary. Complementary means add up to be 90 degrees. So the complementary angle is 90 minus 30 is 60. So if I shot it at 60 instead, same speed. I'm trying to show it the same speed. If it go up and hit at the same spot, same delta x. Okay, so complementary angle 60 and 30 will give you the same range. Now, which one will take a longer time to get there? The higher elevation, the 60-degree one. 30-degree will take a shorter time. Which one will go higher? The 60-degree one. Okay, so what if I asked you, I shot something at 25 degrees. Which other launch angle can I provide that will give me the same range? Well, 90 minus 25 is 65. 65 will give me the same range, but will take a longer time because it has to go higher. So, which angle? So it's the maximum range, 45 degrees. Which angle results in the maximum height? 90 degrees. But it doesn't go anywhere. How does air resistance affect range? Well, it will make the Vx. It will decrease the Vx over time. And so the range will decrease as well. The more air resistance, the less range you'll get. How does air resistance affect height? Same thing. You have air resistance that's gonna slow you down from getting to the height. So that would decrease your Vy over time, and so your height will be less too. Okay, so this picture here is showing. You can follow it along and see that. 45 gave me the, where's 45? Right there. It gives me the biggest range. Whereas, let's see, if you do 75, it hits here the same range as 15. Okay, now there is an equation for range, which makes life simple for these problems when you're solving these problems. And that's this. R is delta x, but they write it like R, range, capital R. Okay, this is, and basically, it's pretty self-explanatory. But you only can use this if it hits at the same level that it was launched. If it goes like this and hits up here somewhere, like a basketball rim, you can't use that equation. Or if you shoot it off a cliff like this, because it landed at the same place, you can't use this range equation for those cases. You only can do it when the distance is measured over level ground. Okay, so rugby player passes the ball 7 meters across the field, where it's caught the same height as left his hand. So we can use the range equation. What angle was the ball thrown? Initial speed was 12. Okay, so the range is 7 meters. Its initial speed angle was, initial speed is 12. I'm looking for the angle 2 over 10. Don't put negative 10. This is not requiring directions. Okay, so I'm going to cross multiply 70. I'm going to divide by 112 squared. That equals sine of 2 theta. Okay, to get rid of the sine, you got inverse sine the other side. Then you'll have to divide by 2 to get rid of the 2. Okay? So I get theta equals 14.5 degrees. Pretty cool. At what angle should R be going for greatest horizontal range? Well, that's 6 different angles above the horizon. Which 2 throws of these cause the javelin to land the same delta x away? Okay, so they had to be complementary. So 60 and 30 does it. 40 and 50 does it. I don't see that. 70 and 20 does it, because they're complementary. And that's it. So 30 and 60. These aren't complementary. These aren't complementary. Okay, a stone thrown from the top of a tower saying, okay, we already did this. So a stone is thrown from the top of a tower. Siemens and a ball is dropped. Okay? Which one hits the ground? Now, I would neglect air resistance, obviously. So neither. They both hit at the same time. This is a stupid answer. Neither, since both had the same original velocity in the y direction. And a deceleration in the y direction. And the same height they're traveling. The horizontal speed has nothing to do with the vertical speed, because the horizontal acceleration is independent of the vertical acceleration. Okay, so this is VO. This is a launch angle. I should say if at the same elevation that it was released. Okay, so we should be able to do this. There's 30 degrees. This is VO. I think I did this one already. So VOY equals 30 sine of 30. Equals 15 meters per second. And I can find the time it gets to the top. And then I'll double that for the total air time. So you have y at the top is 0. Goes from 30 to 0. I'm sorry, it goes from 15. That's what VOY is. To 0 in that time. Okay, so A equals VF minus VO over T. I'm using the Y components. So negative 10 equals 0 minus 15 over T. So 10T equals 15. Negatives canceled out. 1.5 seconds, but that's the half time. So the total time is 1.5 times 2 equals 3 seconds. Okay, I'll read this one. We'll do both those. And it will do that too. So it's all the above. Okay, let's do this one. Then we'll be done. Okay, so we got all the pictures there. I'll probably have to find VOX, VOY first. VOY is 25 sine of 35. VOX is 25 cosine of 35. Let's do that quickly. Okay, so 20, Y component is 14.3, and the X component is 20.5. Okay, I know AX is 0. I know AY is negative 10. Calculate the time it takes the rock to follow this path. Okay, so really, the delta Y is equal to negative 20 meters. So these are the values I have. VOY is 14.3. AY is, delta Y is negative 20. AY is negative 10. And T is question mark. So I think we can solve this by doing delta Y equals VS squared minus VOs. Oops. Delta Y equals VOT plus AT squared over 2. I'm just using the Y values. Okay, so delta Y negative 20 equals 14.3 times T plus negative 10 over 2 times T squared. I'm going to have to use quadratic formula, sorry. So put this in quadratic form. Negative 5 T squared plus 14.3 T plus 20 equals 0. So A is negative 5, B is 14.3, and C is 20. Okay. Okay, when I plug this into my calculator, I get a negative 1.02. I don't want that one. And I get a positive 3.89. So T equals 3.89 seconds. Now you could do negative B plus or minus squared B squared minus 4AC over 2A and solve that for yourself. Okay, T, where that would be what T equals. So let's try that. Negative 14.3 plus or minus 14.3 squared minus 4 times A, negative 5 times 20. Okay, that 5 times 20 is negative 100 over 2 times negative 5, negative 10. So let's do inside the radical 14.3, oops, 14.3 squared plus 400, and take the square root of that. I got 24.59. Okay, so obviously I want to add it so I don't get a negative number. So minus 14.3, then divided by negative 10. Oh, wait. So I get, if I do the positive number, I get t equals negative 1.03. So don't want that one. So instead of doing that, I would do the negative number. So 24.586. Doing plus 14.3. That's really negative. Okay, I get 38.89 divided by, divided by negative 10. And so that comes out to 30.89 seconds is what I got up there. Obviously, you can see that doing it on your calculator is much, much quicker than doing the quadratic formula on your calculator. So try to figure out how to do that. I can show you if you want with the polynomial function on your calculator.